Hey everyone. Before we get started, we wanted to give some of our friends the opportunity to tell you about their new podcast.
Connecting Earth, science, and people. From AGI, this is Audio Earth.
Audio Earth. I'm Rayleigh.
I'm Joe.
Let's go.
If you enjoy Third Pod from the Sun, check out Audio Earth, a new podcast from the American Geosciences Institute. We've got episodes on volcanoes in Antarctica, fossil footprints, and even insight into the incredible Thai cave rescue from a real-life cave scientist. Audio Earth is now available on iTunes, Spotify, or wherever you get your podcasts.
Hi, Nancy.
Hi, Shane.
All right, today we're talking about something to do with old water. And I know this isn't right, but when I hear the words old water, I'm instantly taken back to my upbringing. I grew up with well water.
Yeah, that was a whole foreign concept to me as someone growing up in the suburbs of New York City.
Yeah, it's so funny because, now I live in the suburb of D.C. and that's very different. But yeah, we had well water and it's literally like this big, we actually had different wells dug on our property. I grew up in rural Pennsylvania and your water can run out.
Yes.
Like it can go away.
It can.
And like your well can dry up. And I didn't actually realize this was a thing until I was in high school and our well dried up.
Oh my God.
And we went through a point where our nearest neighbor, their house is I don't know, maybe like a few hundred like yards away, like through a woods though. We stitched together, like 10 different hoses and literally ran a hose from their house down to our house.
That is pretty ingenious.
And we were force flushing toilets with like 5-gallon buckets.
Oh my gosh.
This is Nancy, this is a view into my life.
Yes. Wow. That I don't think I would have liked that in high school. I would have been like, what is this?
It was definitely I grew up in the middle of nowhere, but like it definitely was still something. Like go to school every day and talking to people like, I had to take a shower at my neighbor's house and I'm force flushing toilets, and even my friends didn't know what this was because I grew up in the country away from the country. So that's what I think of old water, but I don't really think that's what it is.
Well, actually, some of that well water can be pretty old. But what we were talking about with old water, basically, is water that hasn't been in contact with the surface on geologic timescales. We're talking like millions and billions of years. But it's found in mines, that kind of thing. But
okay.
Yeah, it's possible. It's not that far off, actually.
Which doesn't make me feel that great that was going into my body. Welcome to the American Geophysical Union's podcast about the scientists and the methods behind the science. These are the stories you won't read in the manuscript or hear in a lecture. I'm Shane Hanlon.
And I'm Nanci Bompey.
And this is Third Pod from the Sun. Turns out we're not talking about water in my well.
No.
We're not, no. Okay. What are we talking about
That would
today?
be an interesting episode like that.
Yeah, maybe someday.
So actually, I interviewed Barbara Sherwood Lollar, who is a professor of earth sciences at the University of Toronto. And Barbara researches the origin of this old water and what it might mean for life in the deepest part of our own planet, but that also has implications for life on other planets. And so what they do is they go down and work with some of these oldest rocks on Earth, down in these mines, ones that are almost 3 billion years old. So they go down into these mines to find the old rocks and then find the old water. So how do you find this water? How do you know where this water is?
Well, actually, that is not as simple as it sounds because it's an interesting phenomenon. When I first started working in this, it was back when I was a graduate student in the 1980s, and we were actually called in partly by the mines themselves to understand why and where in the deep earth, and because we're talking 2-3 kilometers below surface in many cases. So for the Americans, that's anywhere from 3,000, 4,000 to 10,000 feet below the surface of the planet. As these mines were being developed, they would often encounter highly salty water. In some places, water that was more than 10 times the salinity of seawater. And we were called in the 1980s to try to figure out where this was coming from because it actually can cause some problems for mine operation. The wetness, but more importantly, that high salinity can actually cause an incredible amount of corrosion. And so really, from a corrosion point of view, they wanted to understand where this water was coming from, how much more they should expect to be getting, and why were they getting water in this deep area anyway. But the more we investigated these kinds of places, and not just in Canada, but also in other places on the planet where you have these ancient billion-year-old rocks, so that's in Africa and Fennoscandia and Australia, the more we began to talk to miners, we discovered that the miners were completely familiar with this phenomenon. And in fact, in some cases, going back through the early historical literature. So for instance, if we take a look in the historical literature of the Canadian Geological Survey, you'll find your first reference to this back in 1887.
Wow.
Somebody had noted these highly saline waters, bubbling and degassing waters. But somehow this was something, although so familiar to the people who day to day worked in these mines and tried to get ore out, they all knew this was there. It was something that had almost completely flown under the radar of the scientific community for 100 years. Just had never been investigated from a scientific point of view. So a lot of our work then became building relationships with both the mining companies, but also with some of the miners, current miners and retired miners, and anyone who would talk to us about where they'd encountered these waters. This was our first clue and tip to going out and doing our scientific exploration. We go down, again, we have to adapt ourselves to the life on the day of the mine. So we typically go down with them in the early morning shifts, which might be a drop anytime between about 6:30 a.m. or 8. And then we are underground only as long as the shift change, because we have to come back up when the rest of the mine staff come up. So it's usually a day. And then depending on the travel time, that's how much time we have on site. So for instance, if we're going down to 2 and 3 kilometers, to tell you the truth, we might have most of the day is the travel down and the travel back, and we might only have an hour and a half to 2 hours on site. The great thing is when you are underground, if you like rocks, the underground is great because they're all exposed, and you can really read the story of these rocks as you are underground, and it can be utterly fascinating. I'll just give you 2 examples. If you are underground in mines in the Sudbury Basin in Canada, some of the Americans would be aware of the Sudbury Basin. It was an area that's a highly mined area of the Canadian Shield. And back in the days of Apollo, NASA used it to train their astronauts on what, moving around on a barren rock would look like. So it was part of the Apollo moon training. So sometimes Americans are aware of it for that. Most geologists and Canadians are aware of it because it's a prominent city in northern Ontario. It's got all kinds of things going on in that city. It's very prosperous, but it's also been the foundation of a lot of the mining industry in Canada, because 1.8 billion years ago it was hit by a giant cometary impact. And that impact created the ore deposits, or contributed to the creation of the ore deposits by mobilizing fluids and remobilizing material. And so it's a basin with dozens of mines and a ring around the basin. But the fascinating thing is that if you are underground, you can still see in the wall rock evidence of the impact.
Wow. What does that look like?
Well, if you have a microscope, you can actually see more sophisticated shock patterns in the minerals themselves. But in the wall rock itself, with the bare eye, you can nonetheless see these structures that are pressure responses of the rock to the impact. So that's pretty neat. You can actually look and say, oh my gosh, there, on that wall. 1.8 billion years ago is where that impact. It's like the best way to describe it would be like almost like a fan of striations that you can see.
Oh wow, that must be amazing. Cool. Yeah.
So you really know I'm standing in a place where 1.8 billion years ago the Earth was shattered on the score of 300 kilometers.
So what kind of testing are you actually doing down there in the mine?
What we're usually doing down in the mine itself is the easy stuff. The temperature, the redox condition, the pH, the basic stuff. Then mostly what we'll be doing is taking samples of the water and bringing them back to the laboratory to take a look at both their chemical composition. But then also, I'm an isotope geochemist. So really, in addition to just measuring how much of something is there, what we're doing is taking a look at the naturally occurring stable isotope signatures for the additional information that can give us in this kind of detective story of figuring out where these fluids are coming from and how long they've been there. So typically what we'll do is we look like we're going camping. We've got backpacks, similar to what you'd see for canoe camping, and all of the equipment we try to keep very self-contained and in the packs, so that if we do need to walk fairly long distances, we absolutely can be independent and carry what we need to carry with us. And typically it can look very sophisticated. We have to have some gadgets that are quite, little blinking lights and sensors and things. But a lot of the other material looks very unexotic. A lot of what we're doing is trying to hook up samples to flowing fractures or flowing boreholes. So we're carrying a lot of plastic tubing, a lot of bottles, a lot of vials, a lot of pretty unsophisticated looking scientific equipment, but it's what allows us to, in fact, form a seal around the borehole and ensure then that the sample we're taking isn't contaminated, for instance, by mine air or something like that.
Oh, okay.
It's a lot of plumbing.
I think I asked you the other day, how fast is this stuff flowing? Is it like gushing out, or is it like a quietly moving stream?
It's a little bit of both.
Okay.
There are places where it is literally gushing out, where you can't do this work without getting wet. But that's probably not the normal. Normally, these flow rates do decrease over time. So they might start gushing out, but then they'll decrease a bit and be. So then we're interested in no matter what, whether it's a gusher or whether it's something that's just sort of gently trickling out. It's all of interest to us because what we're trying to do is get the broadest possible understanding of the diversity of these waters that are out there, and do that from a geochemical point of view to understand, again, where they're coming from and how old they are, but then also working with colleagues who are microbiologists, take samples to understand what might actually be living in these kinds of fluids. And so in these old waters in South Africa, on the order of 25 million to 100 million years old, we were actually finding our first indications of extremely old noble gases, and specifically looking at neon. Well, it's the same stuff that they use in neon lights, but in this case this was neon produced in the crust and stored in the waters. And we were able to identify that neon was more than 2 billion years old.
Okay, I know that we all learned this at some point in school and scientists, and I should know this and all that, but what is a noble gas?
Well, I am a chemist.
You are a chemist. I didn't forget this time. Yeah, unlike previous episodes.
So a noble gas is basically, an unreactive gas. It's one of those gases that doesn't react as much as other elements. So they Barbara uses that. Scientists can use that gas to figure out how old things are because it hasn't been reacting with other things. And she talks a little bit later exactly about how they do that.
Okay.
So it was a whiff of a very ancient material in water that's old, but there was an indication of something even older. And so I was able to convince them to come to this site I've been describing to you, the one that's 2.7 billion years old, ancient ocean floor, because it's one of the most well-preserved parts of the 2.7 billion year old rock. 2.7 billion year old rock has been through a lot, right? It's been metamorphosed, it's been deformed, it's been uplifted. So normally there's been an awful lot of churn. But this particular site is very well preserved. It's known to be well preserved. And so we went there to test the hypothesis. If we found something that's this old within South Africa, then we could figure out, not only confirm the South African results, but perhaps push it back further by going to a site that's extraordinarily well preserved. And I think you'll find some quote from me saying, well, it'll be millions of years old, but it'll never be billions of years old. But we went and took the samples, and then I got a colleague of mine at Oxford involved, Chris Ballantyne, and I sent the samples off to him and waited a little longer than usual. And I remember vividly calling him up and saying, hey, it's taken a while. How are those samples going? And he said, the mass spectrometer's broken. These numbers can't be right. And so I gave him a little bit more of the context on what the issue was, and says, look, send the data anyway, and let's take a look. And yeah, sure enough, there was nothing wrong with the data. It's just it was showing us It was breaking every record for most radiogenic helium, most radiogenic neon, most radiogenic argon that had ever been identified in the crust.
So what do you mean by radiogenic?
Radiogenic means, I mentioned there are three sources of noble gases. Comes from the atmosphere, comes from the mantle, or this thing we call radiogenic. Now, most people are very familiar with what radioactive means. It's something that's got a half-life, it decays. This is different. Radiogenic reactions are the reactions that take place, I tend to try to say, as a byproduct of radioactivity. So, for instance, if you have a radioactive reaction, like the radioactive decay of uranium, thorium, and potassium in the crust, they produce, as a byproduct of those radioactive decays, radiation, alpha particles, beta particles, gamma particles. What we don't often think about is the fact that those then bounce around down there and they trigger other reactions. So those other reactions are the radiogenic reactions.
Okay.
That's again, a simplified way of looking at it. But essentially what that means is that a lot of these, there are certain categories and certain isotopes of the noble gases that are produced in the rock, in the crust, over time, as a function of those radiogenic reactions. And so they are not themselves radioactive. They don't provide a half-life the way most dating tools do, but they do provide a means of getting a sense of the residence time or date of a system, because the longer a water or a rock is in the crust, the more these build up.
Okay. So how much you have can
Right.
tell you a little bit about how old.
Exactly.
Okay, got it.
It tells you a lot about how old.
A lot.
So using the five noble gases, we're able to get then independent lines of evidence for exactly how long these were. And indeed, these were radiogenically rich in noble gases in a way that had just never been seen, broke every record. And if then you take that, you do some modeling to try and understand what that means in terms of an estimated residence time, and this is where we ended up with residence times for these fluids of more than 1 billion years.
So when you realized that, when you were like, we're seeing things that we've never seen before, this could be the oldest water, it was the oldest water, I guess, that someone had
Absolutely.
seen. And what did you say? What did you feel? What did you...
I think there was a certain amount of tequila involved. I can remember we were all, the team was all meeting together, and we had a big discussion and a lot of excitement. But here's the other important point. That was 4 years before we published.
Wow.
Because when you have such a game-changing result, it's not only your responsibility to ensure that you've nailed every possible piece of the puzzle. Frankly, it's also something that you wake up in dead sweat at night, right? Whatever it's. So we did that. We allowed ourselves to take the time to wake up in the middle of the night and think, wait a minute, let's just test this one more thing. And literally, at one point, we almost had the paper submitted, and then we decided, no, we wanted to test one more thing. And so there's about 9 lines of evidence in this paper, both direct and indirect, all of it supporting the antiquity of these waters. Because this really did change in quite a quantum way our understanding of how old water can be, of how long it can actually be stored in the crust if you do have a highly preserved part of the crust. And so it really behooves you to get that right. But I think that the compelling thinking had been, and is that these rocks had simply been through too much for any of the water to still contain its primary characteristics. So I think that's the key thing. You could find water in these systems, but it was assumed it must be young. It must be water that's come down from the surface much, much later, probably due to fracturing. And indeed, that kind of water does exist. But what we now know is, in addition to that, you can have water that largely has had its history associated with the rocks, and in fact has been out of contact with the surface on geologic timescales. And that, of course, became important then when one begins to think about the nature of water on other planets like Mars, where Mars, of course, having lost any plate tectonics, there's some debate about the degree of magmatic or volcanic activity on the planet at the present time. But what we know is it's not substantial. So one of the questions is, what's the potential for fluids to be stored in the subsurface of Mars on a long time scale as well? And so being able to show that waters could be preserved on multi-billion year time scale in the ancient rocks on this planet means that that is entirely likely that deep within the subsurface of Mars you have similar kinds of fluids. And when you understand that those fluids are energy rich because of the degree to which they interact with the rock, they're full of things like hydrogen and sulfate that are electron donors and electron acceptors, it means that they are a habitable environment. And this is why it comes back to the microbiology. I mean, having determined that these, at least on the Earth, are habitable environments, we're now trying to understand the extent to which they're actually inhabited, and have been doing that around the world for a number of years now.
She's been talking a lot about this work here. It's finding this really old water on Earth, underground and everything. But this has implications beyond us, like beyond Earth, like out into other planets, solar system, etc., right?
Right. So if they can find life in these deepest parts of our own planet, they can then start to look where, or understand if life might be present in some water that's buried on these other planets like Mars.
Or like a moon, like Europa Report.
Europa Report!
I know, like I was pleasantly surprised about how much I enjoyed that movie.
It was good. It was scary.
Yeah. Do you think life on another planet would be like a cephalopod? Like it'd be some sort of squid or
They were like
why
these
not?
weird squids, right? That came out from under the ice.
Yeah. Why not?
Yeah.
But okay, so there's implications out there, out in the universe. But what's it like for what's it like back here as well? I mean, does a lot of this work and this old water and talking about different communities and like miners and other folks like that.
Yeah, so it's been really cool for her, I think, working with these mining communities, miners, because they've been wondering what this old water is all these years.
Mm-hmm. Yeah, I mean, I come from a mining community, so I assume they probably have a lot of the similar questions.
So the community side of it's been really fun. I mentioned to you earlier that because although scientists had sort of become oblivious to this phenomenon was just not understood, miners had known about it for years. And I can remember vividly, shortly after the paper was published, being in my office late on a Friday, and the phone rang, and this voice said, "I'm trying to reach that lady." And I'm a nice person, so I thought, it's probably a wrong number. But I said, well, can I help you? I mean, who are you looking for? And he said, the lady with the old water. And I thought, it is. So it was a retired miner who was living down in Florida now, but he'd worked years and years before way up in northern Ontario. And he said, the stuff was sloshing over our boots all the time, and we couldn't figure out why was it there? Why was it salty? What the heck was this? And he was in his 70s or 80s by then and was just thrilled to bits to know that we'd finally figured something out about this stuff, because they'd been living with it every day their whole professional career as miners. So it really is fun to have those community interactions around your science, not just at the output end, but again, as I mentioned, at the input end. A lot of times we wouldn't know about these localities but for the conversations that we have with the people who are working in them every day. So that's a really fun part of it for us, is that interaction with the mining community.
So I guess this makes you think pretty differently about your own well water growing up.
Yeah, I'm gonna have to when I go home talk to my parents about it and see if there's any cephalopods in there.
Hopefully not.
All right, folks, that's all from Third Pod from the Sun.
Thanks so much to Barbara for sharing her work with us.
This podcast is also produced with help from Lauren LaPuma, Josh Spicer, Olivia Ambrosio, Liza Lester, Katie Brondell. And thanks to Kayla Surrey for producing this episode.
AGU would love to hear your thoughts on our podcast. Please rate and review us on Apple Podcasts. Listen to us wherever you get your podcasts, and of course at thirdpodfromthesun.com.
Thanks all, and we'll see you next time.